All right, so we're going to look at another example here. Essentially, we're going to walk through our 6 steps. This is the circuit. We're interested in I of t, which is the current in this branch over here, which specifically is the inductor current. Okay, so I've called this resistor here the 4 ohm resistor. I've called this guy over here R1. I've called the resistor in this branch over here, I've called that R2. And I've called the resistor in this branch over here R3. So I've written those guys out. Now notice I gave them the names V4, V3, and V6 for their values. Now before I start any problem like this, I'm going to want to usually, for me, define some of the key constitutive relationships. So using my positive sign convention. So I'm looking at this guy and I'm going to say, well, V4 here, V4 looks like it would be what I've defined as I4 times R1, right? Because I got a positive current going into the positive sign, okay? Then I have, let's see, for the other resistor R2 there, I have V3 is the voltage across it, equals IC times R2. Now notice I said IC because that's what I called the current going through that branch. And then I have V6, and that 6 ohm resistor is I times R3, okay? All right, so I've made those definitions. And I also want to put for the inductor and capacitor. So for the capacitor, I have I sub C equals C dV dt, because the capacitor voltage is written here just as V. And I have that for the inductor, VL equals L di by dt, okay? Now that's basically just writing out my passive sign convention stuff. That's going to be important as I go through this problem because that passive sign convention stuff is always important. All right, so step 1, find the differential equation for t greater than or equal to 0. So I posted for you guys some summary slides. It's basically saying in step 1, I specifically want to analyze the circuit after t equal to 0. Leave the L's and C's as normal. Don't short them or open them or anything like that. And then write your differential equation using some combination of KCL and KVL and get it in that form. All right, so in this case, after t equal to 0, that switch opens up. And so the only thing that I really have left, if I do that, I guess I can leave this 10 volts in here. But I see that the 10 volts doesn't matter because there's a break with that switch open, okay? And so the key part of the circuit here is, here's voltage on the capacitor. There is the voltage V3 on R2. And then over here, there's the voltage V6 that's on R3. And there's the inductor here, which has a voltage VL. Now we've had a few things defined for us. The current I is this way. I'm going to leave this so that, just to be super clear, there's another branch over here, but there's no current flowing in that branch because there's a break. So I'm just going to remove it, right? It's not going to affect anything here. All right. So I really just have this one loop that I have to worry about. And I got to remember I defined the current I sub C as going that way. Okay. All right. So let's do a KVL around that loop. So we'll do a KVL. So 0 equals, and I'm going to go in a clockwise direction. So minus V3 minus V plus V6 plus VL, right? So I went minus the plus, plus to minus. Okay, so that's good. I've got that written out. All right, then I keep going with this. I say 0 equals, so minus V3. So I just go straight to my constitutive relationships and start plugging stuff in. So minus IC times R2. That was my V3. All right, my V is just the capacitor voltage. Just going to leave it that way. V6 is I R3. And VL is L di dt. Now remember, our goal was to get to a differential equation for I of t. So right now, 2 of the terms have I in them, and 2 of them don't. So I got to try to fix that. Now, one of the ways I can start with this is I have an I sub c in this right now. And if I look at this circuit, I sub c and I are going in different ways. So I'm going to say I sub c equals minus I, right? Because they have to be the same current. They're just defined to be going in different directions. So that means that that's good because it takes this first term and makes it positive and brings I in. So I have R2. So now what I'm going to do is I'm going to group these two terms. I'm not going to group them yet, actually, just to make sure you guys see it, right? So this guy becomes IR2 minus V plus I times R3 plus L di dt, okay? Now, I got one other thing here, which is that capacitor voltage. Now, one thing we saw here is that IC equals C dV dt. But since we know that IC is equal to minus I, this guy is also equal to minus I. Now, if I want to bring I into this expression, what I need to say is that minus I, or IC, right, is equal to C dV dt. The relationship that I use here is I basically say that the voltage is equal to 1 over C times the integral IC dt, which means that the voltage is minus 1 over C integral I dt, like that, okay? Because of that relationships between the currents. So I plug that in over here, and now I'm going to group this term and this term. So I'm going to say I have I times R2 plus R3 plus 1 over C integral I dt. So the minus and the minus made a plus, okay? So this minus meaning, and this minus made a plus. All right, and then I have the L di by dt. Okay, so at this point, I got to take the derivative of both sides. So I say derivative of this side equals the derivative of this side. So I times R2 plus R3 plus 1 over C integral I dt plus L di dt, like that. Okay, so I take the integral of each of those terms. The integral of 0 is obviously 0. All right, so the only thing that's a function of time in I times R2 plus R3 is I, so I get R2 plus R3 as a coefficient times di by dt. Plus, I take the derivative of an integral. Derivative of an integral just becomes, they cancel each other off, right? So I get 1 over C times I. Then I take the derivative of a first derivative, so that becomes a second derivative. So I get L d squared I by dt squared. Now, I need to get that in my standard form, which up here says I want a unity coefficient, or a coefficient of 1 on the second order term. So that means I divide everything through both sides, right? Both sides get divided by L, like that. And I say 0 equals, and I'm going to reorient things here, d squared I, and we're not calling it I sub L here, just I, d squared I by dt squared plus R1, sorry, be careful about this. It's R2 plus R3, R2 plus R3 divided by L times di by dt plus 1 over LC times I. That is in my standard form, where I call this guy my coefficient A, this guy my coefficient B, and this guy is my coefficient C. So if we look then at what I do here is I go through and I enter this in MATLAB, okay? So I specifically, what I do is I put in what the values are. So these are all the values, all right? You can check those from the circuit. And then I wrote in here, A equals R2 plus R3 over L, right? B equals 1 over LC, and I've got everything entered. Now my step 2, right? If I look at my process here, my step 2 is to basically go through and say, well, I want to get the roots of that characteristic equation that go with that differential equation. All right. And so what we said is I can calculate those roots straight away, or I can use some of these formulas to sort of remember these values of alpha and omega naught, which are included in those roots. So what we said was alpha is a over 2, omega naught is the square root of b. Okay. Omega naught is the square root of b. So I just put those values in here. This is step 2, right? So I go through and I do those calculations. So what I'm going to do is I'm going to run this in MATLAB. So I'm going to look at that result. And I see that alpha is 9, omega naught is 10. So alpha is 9 and omega naught is 10, right? So if I have a situation where alpha is less than omega naught, I need to determine is that underdamped or overdamped. So what I do is I go to my solution types here and I say, well, alpha is less than omega naught. That's what I have in this case. So that means I have an underdamped case where I have 2 roots, and my form of the solution is this guy. So I now know that I of t has to have the form of this expression here. So I of infinity plus e to the negative alpha t times a1 cosine omega dt plus a2 sine omega dt, like that. All right, now it's my job to figure out at this point, what is I of infinity, what is A1, and what is A2? So I can figure out right now what omega d is. Yes, you can. Omega d is equal to square root of omega naught squared minus alpha squared. I can figure out that frequency. All right, the way I do that is I go to my MATLAB script and I've got that written out here. Okay, I'm not going to calculate that right yet because I don't really need it for anything. We'll do that later. Okay. Okay. All right, that's step 2. All right, step 3 for me is to say I need to find the steady state values in IL of infinity and VC of infinity. So I basically need to look at the circuit that exists after t equal to 0. All right. And I need to open the capacitors and short the inductors. That's what happens, we said, if we wait long enough and we reach steady state, that our capacitors become opens and our inductors become shorts. So we need to find VC of infinity and IL of infinity. All right, so let's do that. So we need to go back to the full circuit here. All right, so let's go back to the full circuit. Here it is. Okay. And we got to say, after this switch opens up, let's look at what happens in the steady state scenario. So basically, this was our circuit after t equal to 0, what we drew right here. So if I take that circuit and I simplify it down, right? So in step 3, this is actually a pretty easy step usually. I have the capacitor gets replaced by an open. So here's V of infinity. There's a voltage across an open, right? And I have my 2 resistors, and then I have my inductor gets replaced by a short. So if we look at that, there is no sources at all in that circuit, right? So I can tell right off the bat that I of infinity, which we said was going this way, right? I of infinity has to be 0, and V of infinity similarly has to be 0. There's no sources in that circuit. Long after steady state, there's going to be nothing happening, no energy stored in that circuit, no sources, nothing's going to be going on. So I'm done with that. So now I got to go to step 4. Step 4 is to find my, analyze the circuit at t equals 0 minus to get my initial conditions. And I want to get the initial conditions on the capacitor voltage and the inductor current. All right, now at t equals 0 minus, what we said is going on is, and let me pull up my summary slide here. Right, at t equals 0 minus, we assume the circuit was in steady state for a long time before t equal to 0. So that means we open up the capacitors again and short the inductors, but we do it for the circuit before the switch moves. All right, so before the switch moves. So before the switch moved, if I looked at that circuit right there, let me zoom out a little bit, right? If I look at that circuit, I'm going to do this over here, I guess. I've got this voltage source here, this 10-volt source, and I've got this R1 at 4 ohm resistor. The switch is closed, so at t equals 0 minus, the switch is closed, right? Now the capacitor has been charged for a long time, so we're going to say it's an open. So this is V0 minus. Got this resistor hanging out here. Okay, here's R2. Now on this branch, I've got my 6 ohm resistor, which I called R3, and my inductor is a short. So we'll call this IL0 minus, like that. Now, if I look at that, one of the things I can see right off the bat is there better be no current in that guy right there, right? There's no current in that open circuit. So that means there's no current in that branch with R2. So I can see right now that IL of 0 minus, there is current in that outer branch. IL of 0 minus is going to be 10 volts divided by R1 plus R3. And if I look at the capacitor voltage, because there's a current flowing in this outer loop, I basically have a voltage divider, and V of 0 minus is going to be the voltage across R3. Now, it may be hard for you to see that the voltage 0 minus, right, that voltage which is defined across this open, may be hard to see that that's the same as the voltage across R3, but if you do a KVL around this loop over here, right, this loop on the right side, you'll see that if there's no current flowing in R2, there's going to be no voltage drop across it. So V0 minus is going to be R3 over R1 plus R3 times my 10-volt source. Okay. So what I do is I put those into MATLAB. All right. So here's the two expressions I used, and I define V as 10. So if I run those real quick, I'll see what those values are. I see that VC of 0 is 6 volts and IL of 0 is 1 amp, right? So IL of 0 is 1 amp, and this guy is 6 volts, okay? Pretty straightforward and easy to calculate, okay? All right, so now I'm almost done with step 4. The last part of step 4 we said is, you know, if I look at the more detailed values here, we said that the capacitor voltage and the inductor current always have to be continuous. So what we say is that right before the switch moves and right after the switch moves, they're equal to each other. So that means that V0 plus is 6 volts and IL of 0 plus is 1 amp. Okay. All right. Now we need one more thing, right? In order to get the unknowns in this equation, right? Our whole goal was to figure out what I of t looks like. In order to get those unknowns, I need to get an initial condition for the derivative. Okay, so basically what we said here in step 5, all right, if I go to my step 5, I move the switches, all right, I move the switches to wherever they should be after t equal to 0. Then I replace my inductors with current sources, and I replace my capacitors with voltage sources. Solve for IC and solve for VL, and then use those values to get the derivatives, okay? So we're going to move the switches, replace our inductors with current sources, replace our capacitors with voltage sources. So we know that after the switch moves, the circuit looks like this, okay? After the switch moves, the circuit looks like this. So if that's the case, we're going to say I have V of 0 plus. I have a resistor, which we define to have a voltage V6 like this. And the inductor is here, right? So we say this guy has IL of 0 plus. And then there's a resistor here. This guy is R3. This guy is R2. All right, so here's, we call this V3, call that V6. Like that, okay? Now, what we need to do is we were supposed to find VL of 0 plus, right? That's the voltage across the inductor. and the capacitor current. Now, the thing I want to look at with the capacitor current is we defined originally, back to our original circuit, we defined the capacitor current to be going down that branch, okay? So when I look at the circuit here, I look at the circuit in this condition, I better set this up so this is IC 0 plus, like that, okay? So one thing I can see off the bat, right, is that the current in this circuit is, first of all, is fixed. It is fixed at the value of IL 0 plus, right, because I have a current source. I have a current source pushing current through that loop. So the current in every device here is IL of 0 plus, which was 1 amp. And that is equal to minus IC of 0 plus. Now I know it's got to be equal to minus that because I've defined the current to be going in the opposite direction, right? Which means that that capacitor immediately starts to discharge, okay? So I have now the value of IC 0 plus. The thing I got to do now is figure out what VL of 0 plus is, which that's going to have to take a KVL. All right, so I'm going to do it this way. I'm going to say 0 equals minus V3, right, minus V0 plus. So I just basically continue like I always did, right? I use the definitions of voltage I did in the beginning, minus V3. When I say what I did in the beginning, if I zoom out here and zoom back in over in this corner, right? Notice I'm keeping consistent with the definitions that I made at the beginning. I need to stay consistent with those definitions, right? So minus V3 minus V of 0 plus V6 plus VL of 0 plus, right? Just go around that loop. Now my goal is to figure out VL of 0 plus. So I can see here that VL of 0 plus would have to be equal to V of 0 plus minus V or plus V3 minus V6. Now what I'm going to do is I'm going to go back over to my relationships, right? V6 was defined in terms of the current, right? V6 was defined in terms of the current flowing into its plus terminal, which we called I. V3 was defined by the current flowing into its plus terminal, which we called IC, okay? So that means V0 plus is just a value, right? So I'm going to leave it as V0 plus. We know that value. We solved for it. It was 6 volts. V3 is plus IC of 0 plus times R2, right? Because we defined it in terms of I sub C, and I sub C goes down, okay? And then I have minus V6. So minus V6 was defined as minus IL times R3, okay? This is really important here, right? We got to watch, be careful of these signs. Because IC is equal to minus IL, this guy becomes V0 plus minus IL of 0 plus times R2 minus IL of 0 plus times R3. Now, if I go through at this point and do that calculation, what I find, and I've got that here, right? Go through and do this calculation right here. What I'm going to get is -3. So what I'm going to do is I'm going to run this whole thing. Okay, run that whole thing. Look at my answer. I get VL of 0 plus is -3. IC 0 plus is, I should be careful, it's minus IL 0. Okay, so this guy is equal to -3 volts. And IC of 0 plus is -1 amp. Now that I actually don't turn out to need in this particular case. Now the last step, right, is to find DIL by dt at 0 plus. So I say DIL by dt at 0 plus is equal to VL at 0 plus divided by L. So that's -3 divided by L, right? And I'm going to let MATLAB calculate that for me. All right, that's my step 5. Now I'm done. I have everything I need. My step 6 is to combine everything, okay? So my step 6 I had, if I go back to this guy here, I have my I of t is equal to my I of infinity plus e to the negative alpha t times a1 cosine omega dt plus a2 sine omega dt, like that, okay? And I know that I of infinity now is 0, all right? My job is to find a1 and a2. And I also know at this point that I of 0 is equal to 1 amp and di by dt is equal to minus 3 volts divided by L. Okay, whatever that is. All right, I need to figure out what that's going to be. All right, I just need to plug in L to figure that out. So what I do is I basically say, all right, I'm going to take this expression right here. And what I do is, remember we plug in t equal to 0 into I, and we plug in t equal to 0 into the derivative, and we simplify those expressions, right? So what I did was I gave you what that looks like, right? So in the case of underdamped, right, we took the derivative, we plugged in t equal to 0. I have these results right here, all right? So I'm going to put these two things next to each other. All right, the way that I do this is I say I of 0 equals I of infinity plus a1. That's one equation with one unknown. Very easy to solve for a1. All right, and di dt of 0 equals minus a1 alpha plus a2 omega d. Okay, so what I do is I always say, well, I take that first equation and I turn that into I of 0 minus I of infinity equals a1 plus 0 times a2. And I have di by dt of 0 equals minus a1 alpha plus a2 omega d. And remember, I try to turn that into a matrix equation where the first line, all right, that first equation looks like this: 1, 0, a1, a2, like that. And the second line there becomes di 0 by dt, and that's equal to minus alpha and omega d, right? So if I multiply this out, negative alpha a1 plus omega d times a2, and then I can solve for that. So what I was saying was I called this y, I call this c, I call this a, all right? So that means that a equals c inverse times y. Okay, so in my MATLAB code, what do I have? All right, so my MATLAB code, what I did was, okay, so here's the y matrix. IL of 0, that was my initial condition, minus I of infinity, right? So that's this guy. Then I put a semicolon in here in MATLAB to get me to the next line, and I put in the initial condition for the derivative, which I called DIL, okay? Then I enter this matrix here, which I called C, right? So it's 1, 0, that's my first row. Then I put a semicolon to go to the next row, and then I have minus alpha and omega d on my second row, okay? So at this point, then I say A equals inverse C times Y, right? So if I do that, I'll get the values of A1 and A2. So let's just take a quick look at what that looks like, all right? So if I take a quick look at what that looks like, I get A of 1, the first, and this guy has 2 entries. So if I say A of 1, that's 1. A of 2, that's the second entry. That should be 0.6882, and it is, okay? So that means if I go over to this expression I had here, right? This was the expression, e to the negative alpha t, blah, 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 right? I now know what the values of everything is there, okay? So what I do is as I've said, I'll always give you a t vector, okay? And then what I did was I created the I vector here, right? And I gave you, if you look at my MATLAB here, I gave you the formulas for each of these, okay? What I've done is I've put in the formula specifically in this case for the underdamped. So I've said I of infinity, which is my steady state value, plus e to the negative alpha t. We said we do e with exponential, exp. Now the key thing is, this is a MATLAB issue. This is going to be a series of numbers because it's defined at a series of times. So we do a dot multiply, right? So again, you don't need to know all the details of that, but essentially in this particular case, if you look at what I gave you, again, I will never ask you to do anything in MATLAB that I haven't already given you. There's a dot multiply here, dot multiply, and then I have a of 1 times cosine omega dt plus a of 2 times sine omega dt, right? So what I'm going to do is I'm going to take that whole thing and I'm going to run that now. And there it is. All right. So I see, just like I expected, my current starts up here at 1. That's what we had expected. That was our initial condition. We said it had initially a negative derivative, right? So I see that he's starting to head downwards as time advances. That's a negative derivative, right? A negative slope. And then he heads towards 0 as time advances. Now we said he was underdamped, and at first glance, this doesn't necessarily look fully underdamped, right? Underdamped would mean I have some overshooting, where I kind of go past my final value. So in other words, I would go below 0 and then back towards it. In this case, it does happen. If I zoom in, which I can do here, I can see there's a little bit of that overshooting behavior where he goes, a couple of milliamps below 0 and then back towards it. All right. So it's not a lot of underdamping in this case, because in reality, the alpha and omega values, if you remember here, alpha was 9, omega naught was 10. That's just a lightly underdamped system, we would call it. So it doesn't have a lot of overshoot going on. But again, that's another good example of how to go through that process.